Hi everyone, today we're going to continue our discussion on the different types of equations like molecular, complete ionic, and net ionic equations. So what we're going to do is we're actually going to go through an example and we're going to look at how we write each of those equations and how we break everything down. So consider the following reaction. Potassium chromate plus barium nitrate yields what? So first what we have to do is we have to write our reactants as symbols. So if we take this potassium chromate, this just works with our naming and with writing formulas. Potassium is K+. Chromate, this is one of the polyatomic ions that you need to make sure you know because you're going to find that we're going to use it quite often. We have K+, CrO4 2-. If we crisscross, K2 CrO4. We have potassium chromate plus barium nitrate. If you remember, barium is Ba2+, nitrate NO3-. A barium, find off the periodic table. Nitrate, again a polyatomic. If you crisscross, you get Ba NO3-. So what we have is we have our reactants as symbols. Now what we need to do is include states of matter. Well, this is where your solubility rules come into play. If you remember, anything with potassium, nitrate, ammonium, and sodium are always soluble. So that means this has potassium. If it's soluble, you write AQ for aqueous. Aqueous means it's dissolved in water. And then barium nitrate. Nitrate, anything with nitrate is also soluble. So we have potassium chromate plus barium nitrate, both are solutions. So what we're going to do is we are going to take a look at the reaction itself. So we have potassium chromate, we have barium nitrate. We can actually predict the products. You have two solutions being added together. This is a double replacement reaction. Your positive ions switch. Remember, whenever you form a new compound, you have to use the crisscross method. Make sure that your charges cancel out. So we get barium chromate plus potassium nitrate. Notice there's a 2 in front of the potassium nitrate. We have to balance our equation. So again, remember, anything with potassium and nitrates will break apart into ions. They always are soluble. If we look at this, we can now predict states of matter for our products. I just said anything with potassium nitrate is soluble. That makes this aqueous. Then think about your solubility rules. Okay, you have to memorize these solubility rules, so think about these. You will find that barium chromate is insoluble, which means it's a solid. Okay, again, barium chromate is insoluble, that makes it a solid. Now this overall equation is what we call our molecular equation. Our molecular equation gives the overall stoichiometry of the reaction. Okay, again, this gives the overall stoichiometry, but it doesn't show the actual forms of the reactants and the products in solution. It doesn't give us the correct picture of what actually occurs in solution, but we can then take this a step further. So if you were to put these two solutions together, potassium chromate is a yellow solution, barium nitrate is a colorless solution. If we put these together, we find that we form a yellow precipitate in solution. Now, if you think about what I just said, what do you think forms the yellow? This is yellow, this is yellow. It's probably going to be the chromate that forms that yellow color. So what we're going to do with this reaction is we're going to break it down a step further. So we're going to take our molecular equation, which we have here, and we're going to break down any strong electrolyte. Anything that is soluble, we're going to break down and dissociate into its ions. So that means potassium chromate, barium nitrate, and potassium nitrate, we're going to dissociate into ions. All that means is we take what we had and we split it up. We have 2K+, okay, because it was K2CrO4. CrO4 2 minus, Ba2 plus, and 2 NO3 minus. You have to have these coefficients because you have to keep the same number of ions that you had in the formula. And that yields barium chromate plus 2K plus and 2 NO3 minus. Okay, notice all of our strong electrolytes are broken down into ions. We can also notice that we have some similar ions on the left and on the right. If you notice, we have 2K plus on the left, 2K plus on the right. Well, like math, if we have the same variable on the left as on the right, we can cancel it out. So we have 2K plus here, 2K plus. We're just going to cancel these out. If we follow through, we find we have 2 NO3 minus on the left, we have 2 NO3 minus on the right. So we just canceled out ions that were similar on both sides. Okay, what these are is these are spectator ions. These are ions that don't participate in the overall reaction. They remain ions from the reactants to the products. So these are our spectator. They kind of just sit back and watch. What we had here is our complete ionic equation. In the complete ionic equation, all of the strong electrolytes are dissociated. Okay? This reveals that only some of the ions participate in the actual reaction. Because if we notice, we only have a few things remaining that we didn't cancel out. So what this shows us is what we call the net ionic equation. The net ionic equation shows the ions that participate in the reaction. So the net ionic includes only the participating ions. Now, AP loves to ask you to write net ionic equations, so get into the habit of writing these net ionic equations for every reaction if it's possible. Okay, so in this case we have the chromate ion plus the barium ion makes barium chromate. Notice everything is still balanced out. We had 2 potassium ions cancel out with 2 potassium ions, 2 nitrates and 2 nitrates. We can't add or take away any mass. The law of conservation of mass still takes place, still occurs in any net ionic equation, but we can just make sure 1, 1, 1, and 1. This is our net ionic equation. And so just to kind of summarize what we did. First, write a balanced equation. Okay, that's your molecular equation. So write it like you normally would, include states of matter, balance it, and then dissociate all strong electrolytes. When you dissociate all of your strong electrolytes, that gives you the complete ionic equation. This allows you to actually paint a picture of what is actually occurring in solution. Then cross out anything that is the same from the left side to the right side. Any ions that remain consistent throughout, these are your spectator ions, cross them out. Then finally you can write the net ionic equation with the species that remains. So from all of this, you get the net ionic equation, which shows you exactly what happens in solution. Typically it's going to be a formation of a solid, but you could also have the formation of a liquid as well.